Let's show that a polynomial of degree 3 has at most 3 real roots. A root is a solution to the equation f of x is equal to 0. And we're trying to show that there are at most 3 of these. In order to show that there are at most 3 real roots, we need to show that there cannot be 4 real roots. Since this says at most 3 real roots, we're okay if there's 0, 1, 2, or 3 real roots. So we don't need to show that there's at least 3. We only need to show that there cannot be 4. There's at most 3, so there's not 4. To do this, we're going to use Rolle's theorem. So let's start with the hypotheses that we know are already fulfilled just by having a polynomial of degree 3. So a polynomial of degree 3 which we're going to use f of x is equal to ax squared. Nope, cubed, degree 3. Ax cubed plus bx squared plus cx plus d. I'm using capital A, B, C, and D for the coefficients because later on for some of my solutions and inputs, I'm going to be using lowercase letters. And rather than using the whole alphabet, I'm just going to use some uppercase and lowercase letters. So back to our hypotheses though. A polynomial of degree 3 is continuous on the interval negative infinity to infinity and differentiable also on the interval from negative infinity to infinity. Okay. Now we're going to suppose that a polynomial of degree 3 has 4 real roots. This is going to be the beginning of our not terribly precise, but acceptable, since we're just showing, not proving, proof by contradiction, that a polynomial of degree 3 cannot have 4 real roots, because we're going to run into some sort of contradiction. But we'll start by supposing this thing that we are later trying to show is not true. So suppose that a polynomial of degree 3 has 4 real roots. Again, we know this isn't true. We're trying to show that if we suppose this, we end up with a contradiction. Then, if there's 4 real roots, there must be 4 solutions which we will call A, B, D, and E. See, these are the lowercase letters I was talking about. To the equation ax cubed plus bx squared plus cx plus d equals 0. So these are the solutions to this equation. They're the inputs that when we input them into our third degree polynomial, our output is 0. So that means that f of a is 0, f of d is 0, f of e is 0, and f of b is 0. I'm putting my a and b on the outsides of this interval just so that we can use more similar language that we've been using to Rolle's theorem. So since f of a is equal to f of b is equal to f of d is equal to f of e, there must exist three numbers which I will call C1, C2, and C3 on the interval from A to B, such that f of C1 is equal to f of C2 is equal to f of C3, and these are all equal to 0. And this is by Rolle's theorem. There's a couple different shapes that this polynomial could take. It might be increasing first or decreasing first. But either way, if f of a, d, e, and b are all equal to 0, then we must have these three c values, where at each of these inputs, the tangent line's slope is 0. So this is that f. Oh, I forgot all my primes. F primes. So this is f prime of C1 is equal to 0. F prime of C2 is equal to 0. And f prime of C3 is also equal to 0. So let's find what these c's are equal to. So that means that f prime of x is equal to, well, let's take the derivative. So that'll be a 3ax squared plus 2bx plus c. And that means that we're going to have three values, so three solutions, to this thing being equal to 0. Well, since f prime of x is a quadratic function, which have at most two real roots, we have arrived at a contradiction. So a polynomial of degree 3 cannot have four real roots. Therefore, a polynomial of degree 3 has at most three real roots. If you wanted, you could also have solved this for x by using some variable-filled quadratic formula, and you would have gotten to some sort of point where you have x is equal to plus or minus something. but it's enough to say that we already know that quadratic functions have at most 2 real roots. Most of the time, anyway. We're going to look at 2 more problems, because making them their own video seemed a little weird. Okay, so suppose that 3 is less than or equal to f prime of x, which is less than or equal to 5, for all values of x. We want to show that 18 is less than or equal to f of 8 minus f of 2, which is less than or equal to 30. Okay, so we need to connect this f prime of x to this f of 8 minus f of 2. By the mean value theorem, we must have some sort of f prime of c is equal to f of b minus f of a over b minus a. So if we choose 2 and 8 for our a and our b, that means that we have some sort of f of 8 minus f of 2 over 8 minus 2. So we have that f prime of c is equal, I'm going to use a different color, I guess, f prime of c is equal to f of 8 minus f of 2 over 8 minus 2. So we can substitute that in. So we have 3 is less than or equal to f of 8 minus f of 2 over 8 minus 2, which is 6. And this is less than or equal to 5. So we replaced the f prime of x in there. Now let's solve for that f of 8 minus f of 2. So we'll multiply each piece of this by 6. So we have 3 times 6 is less than or equal to that f of 8 minus f of 2 over 6, all times 6, which is less than or equal to 5 times 6. Which means that 18 is less than or equal to f of 8 minus f of 2, which is less than or equal to 30. So if this is true, we can show through this process that the other piece is also true. Now, one more problem. So, does there exist a function, f, such that f of 0 is equal to -1, f of 2 is equal to 5, and f prime of x is less than or equal to 1 for all of x? Okay, so let's try this out. Let's sketch this real quick. So we're given 2 points. We're given the point 0, -1, and the point 2, 5. So we have 0, -1, and we have 2, 1, 2, 3, 4, 5. Oh, I forgot to go over 2. Okay, so let's just, suppose that this function does exist. So suppose such a function exists. And that it is continuous. On the interval between these 2 points. Because if it's not continuous, then we're probably having some issues with that derivative there where it might not exist. And since we know that f prime of x is less than or equal to 1 if this function exists, that means that it also has to be differentiable. on this interval. So since it's continuous and it's differentiable, then by the mean value theorem, forgot my by, there must exist a number c on the interval from 0 to 2 such that f prime of c is equal to f of 2 minus f of 0 all over 2 minus 0. So that's equal to 5 minus negative 1 over 2, which is 6 over 2, which is 3. Now, since f prime of x is less than or equal to 1, but we just found that there has to be some sort of f prime of c that's greater than, well, that is 3, we have arrived, we have arrived at a contradiction. Therefore, such a function does not exist.